Très bien. Okay. Okay, so, well, let's go. Do you have slides you want to share with us?
Yeah, sure. Let me try to share it. It's my first time using this. Let me figure out. Yep. So can you see my screen?
Just a second.
Not yet.
Not yet?
Yeah, okay.
Yep, okay, that's fine.
Okay, yeah, maybe we can start. Yeah, sorry, can you hear me?
Okay.
Can you hear me?
Yeah,
Okay,
yeah, we can
maybe
hear you
we'll
very
start.
well. It's okay, perfect. We
Okay.
see the slides, and so things are okay. Thank you very much.
Yeah, sure. So yeah, hi everyone. It's really honored to be here to discuss about this kind of large language model and knowledge graph with you. So yeah, my name is Linhao Luo. So I'm currently a third year PhD student at Monash University, and my supervisors are these three very awesome researchers. And my research topic is basically focusing on the large language model and the knowledge graph. So today I want to share some insights I have with you about how we can unify the large language model and the knowledge graph together, and how we can put them into the actual applications, and what is the future research direction in this area. Yeah, so this is the three research question I want to address in today's talk. So the first is, what is the strength and the limitation of large language model and the knowledge graph? And the second question is, what method we can use to fully exploit their potential and enhance each other, and how we can unify them in the downstream application. And the last one is, what is the future directions in this area? Let's first start with some background. So, like today, the large language model, like such as the ChatGPT and the BART, are quite popular and powerful, and they can generate very fluent response and making dialogue with the human. And this kind of large language model have a lots of potential that can be used to various of downstream tasks, like question answering or assistant agents. So these are quite popular and powerful tools in nowadays. However, despite this kind of power, despite this kind of powerness of the large language model, there are still some limitation of it. So the first is, the large language model often suffers from this kind of hallucination problem. So in some cases, the large language model will generate the result with some factual error. So for example, when we ask, when did Einstein discover the gravity, the answer might be incorrect. For example, the large language model might reply, Einstein discovered the gravity in 1687, but it's incorrect, right? Because we all know that it's the Isaac Newton who discovered the gravity. So this kind of hallucination problem actually impairs the trustfulness of the large language model, especially when we apply it in some high-stake scenario like medical diagnosis. Yeah, and the second limitation is that the large language model lacks interpretability, because the large language model basically is a black box, and we do not know how they represent their knowledge and how they make the decisions. So when we given an input, we do not know how they generate the output. So we cannot trust its output, and we cannot verify it. And the third limitation is that the large language model are generated by the probability, which means that the next token are samples from probability distribution. And this leads to indecisive results of the large language model. For example, when we ask a large language model we give the same input, the large language model might respond differently. So this kind of behavior is what we don't like in the actual application. Yeah, the last one is large language models are very hungry. There are millions of parameters and require lots of training data. But in some specific domain like medical or legal domain, we do not have a lot of pre-training data to train a domain-specific large language model, so that we cannot easily adapt the large language model to some specific domain. Yeah, so the large language model now are Superman, so who can watch it, who can help us to improve the ability and watch the ability of the large language model. Yeah, we believe the knowledge graph could be a great help here. So the knowledge graph actually stores like enormous facts in a way of triples, which is a structural representation of the knowledge. And here is an example of the knowledge graph that can be extracted from the Wikipedia. We can see that we have lots of triplets, and for example, Obama was born in Honolulu, and Obama was a politician of the United States. So this kind of structural knowledge are quite helpful and can be used as a very reliable source for the large language model. Yeah, so unlike the LLM, which is indecisive, the facts and the facts in the knowledge graph are quite adamant, which is a black and white fact. So each fact stored in it is what it is. It's not a probability that the facts are changed by some probability. So that's a good thing of the knowledge graphs. Yeah, and the second thing is that the knowledge graph is transparent. So all the ontologies are defined and all the facts are stored it. And also the reasoning process in the knowledge graph is quite transparent to the user. For example, we can conduct some symbolic reasoning, or we can run some semantic query. In that case, all the reasoning process and how we get the result are quite transparent to the user. So in that way, we can have an easy interpret for the result generated from the knowledge graph. Yeah. And the third thing is that so the knowledge graph, there are also lots of domain-specific knowledge graph. For example, medical knowledge graph, common sense knowledge graph, or even multimodal knowledge graph. So this kind of knowledge graph can provide lots of domain-specific knowledge that can be very useful for the large language model, especially when we apply them into some domain-specific area. Yeah, so despite the knowledge graph are quite useful, there are still some limitations. So the first major limitation is knowledge graph are very difficult to construct. So especially when there are multimodal data, unstructured data source like the raw text and also like the image. So this kind of unstructured, how to extract information from this kind of unstructured data and construct structural knowledge graph is one of the major challenge in the knowledge graph communities. Yeah. And also the knowledge graph are often incomplete and also dynamic changing. So as the time goes, there are lots of new facts can be added to the knowledge graph, and also there are some facts could be changed in the knowledge graph. For example, for now, the president of the United States is Joe Biden rather than Barack Obama. So how can we capture or represent this kind of new knowledge and complete the and also predict the incomplete knowledge in the knowledge graph is also quite interesting and challenging topics. Yeah. So in this way, we believe that we can synergize the large language model and the knowledge graph together to fully utilize their potential. So when we apply the knowledge graph to the large language model, we can use the knowledge stored in the large language model to address the hallucination and the interpretability problem issues of the large language model. And also we can use the large language model to help the knowledge graph construction and also conduct the reasoning on the knowledge graph. And that's the reason we believe there is a great potential of synergize the large language model and the knowledge graph together. Yeah, so how do we do that? Let's come to our roadmap paper. And in our roadmap paper, we actually give 3 categorization about how we can synergize the LLM with the knowledge graph. So the first one is we call them as KG enhanced LLM. Basically, we want to use the knowledge graph to help the large language model. And the second component is called the LLM-augmented knowledge graph. And in here, we try to apply the large language model to address lots of applications in the knowledge graph. And third one is called synergized LLM and knowledge graph, which we believe is a future direction in this area, and I will discuss them later. Yeah, so here is our roadmap paper. So basically today's presentation only covers like a small portion of it. So if you are interested, and please feel free to read the details in these papers. Yeah, and here is the 3 roadmaps I have presented. So like I mentioned, for the KG enhanced LLM, the structural fact and domain-specific knowledge in the knowledge graph can be used to enhance the ability of the large language model to address the hallucination problems or black box issues. Yeah, and in the second part, we use large language model because it have lots of general knowledge and the language processing abilities. We want to use them to help to address lots of KG related tasks like knowledge graph completion, knowledge graph construction, and yeah, so there's a lot of potential apply the large language model for the knowledge graph. Yeah, and in the third part is that we try to build a synergized model where the large language model and the knowledge graph are stay in equal positions, and it can be used to help each other. And the knowledge graph can provide the factual knowledge, and the LLM can process this kind of knowledge and represent them and help the knowledge graph to understand this kind of knowledge better and also infer some new insights. Yeah. So here is three roadmap we have presented. Yeah. Yeah. So when we try to use this kind of method in the downstream application, we also provide a 4-layer framework. So in here we have a data layer, a synergized model layer, technique, and application. So in the data layer, we can see we want this kind of synergized model can handle like different data from different modality, like the structural knowledge and also the original unstructured text. And if even in the future, with a multimodal LLM, we can even handle the image, videos, and something else, and more data in the models. And in the model layer, we want this kind of synergized model. In here, the LLM and the knowledge graph can enhance each other and better capture the informative information from the raw data. And how, with this kind of module, we can apply lots of existing techniques above it, like the prompt engineering, graph neural network, or in-context learning. So this kind of techniques can be applied in this kind of synergized model to enhance its abilities. And after that, we can apply this kind of model in many applications, like a search engine, recommendation system, or AI assistance. Yeah, and in here we can see that actually for now there are some applications that have tried to explore the ability of both large language model and knowledge graph together, and it also achieve a quite promising result. Yeah, yeah. In the third part, I will go to the details about the roadmap we have presented. So the first one is the knowledge graph enhanced large language model. And in here, we can use the knowledge graph to enhance large language model during the pre-training stage and also inference stage. And we can also use the knowledge graph to enhance the interpretability of the large language model. Yeah, but in today's presentation, I will most focusing on the first 2 parts because if you are more interested in using knowledge graph to provide the interpretability for the large language model, you can refer to the paper for more details. Yeah, so in the pre-training stage, the most naive way is to inject the structural knowledge of the knowledge graph into the large language model by using additional fusion modules. Yeah, basically here is a very typical example, and given a text, for example, a question, and we can easily extract a relevant knowledge graph or a set of triples from the knowledge graph. And for them, we can feed them both into this kind of synergized model. And for the text, we can have the transformer layer, transformer layer. And for the graph part, we can use some existing graph neural network to capture the structural knowledge inside this kind of structured knowledge graph. and then we can fuse them in a fusion module, which in here the knowledge from the text and knowledge from the structure can be interacted with each other, and above this kind of knowledge fusion layer, we can have different. We can have the text output. We also can have the knowledge graph output, and we can optimize them with both the text optimization objects like the fill-in bank or predict the next token. We can also have the knowledge graph training objects like the link prediction or node classification task. So in that way, we try to inject the structural knowledge into the large language model during the pre-training, and after that, we can have like a more powerful large language model with both the text information and the structural information injected into the parameters. Yeah. So despite this kind of knowledge enhanced LLM pre-training could fuse this kind of structural knowledge into the LLM, but the real world knowledge are changing over the time, and this kind of pre-training approach cannot update the knowledge without retraining the module. And also, this kind of pre-training requires lots of computation resource, which is not very practical for some for some companies or for some researchers. So another very interesting topic is called KG enhanced LLM inference. In here, we try to separate the knowledge and the text, and only eject the structural knowledge during the inference. In that way, we can update the knowledge inside the LLM on the fly. So inside this kind of topic, the very popular way is called retrieval augmented knowledge fusion. Basically, given the question, we can have a knowledge retrieval, and we can retrieve lots of relevant facts from the knowledge graph. For example, there are some facts about Barack Obama, and we can use this kind of facts as a context and provide it to the and provide them to the large language model. So the large language model can conduct the reasoning based on this context. And in that way, we can easily inject new knowledge into the large language model without any additional model training. So in this way, this kind of method are widely used in many applications, especially for some question answering systems. So here, and also implement this kind of retrieval augmented knowledge fusion is quite easy. So, and it can also be integrated with many closed source large language model like ChatGPT. So here is a very intuitive example. For example, when we ask, when did Apple announce Vision Pro, the ChatGPT might respond, sorry, I do not have the knowledge after the September 2021, so I cannot answer this question because Vision Pro was released in 2023. So in here we can actually implement this kind of retrieval augmented fusion in a few lines of code. In here we can see assume we have a knowledge graph represent contains all the facts we have about Apple and the products released by the Apple. And with the long chain, which is a very popular retrieval augmented package, and we can given this kind of question, we can easily retrieve the relevant facts from this knowledge graph. In here is the Apple and also all the product released by Apple. And after given this kind of context, the ChatGPT can successfully answer our question, which is Apple announced the Vision Pro in 2023. So this kind of example shows us the powerful of the retrieval augmented knowledge fusion and it's quite easy to implement in the actual applications. So despite this kind of integration is quite popular, there are still some limitations and also some research questions we need to investigate. So first is how can we effectively retrieve the knowledge from the knowledge graph? And here, for existing method, we can use the entity linking or keyword search, but there are still lots of noise and lots of irrelevant information could be retrieved. So this kind of irrelevant information could deteriorate the reasoning of the large language model or even lead to the hallucination problem. And the second question is how we conduct the reasoning based on this kind of retrieved knowledge. So currently, we usually treat this kind of retrieved knowledge as a set of facts, or set of triples. But as we all know, the knowledge graph actually contains lots of structural information. So for example, if we try to conduct a multi-hop reasoning, then a single fact is not enough. We need to like concatenate two facts together to get this kind of two-hop reasoning. So how can we utilize the structural information inside this kind of retrieved fact to fully improve the reasoning ability is also a quite interesting question. Yeah, so here's how we can effectively utilize the LLM for knowledge graph for LLM reasoning. And here is a comparison between the pre-training method and also the KG enhanced inference method. And in order to solve this kind of limitation, so we want to present one of our latest work called reasoning on graph. In here, we use this kind of planning retrieval reasoning paradigm that can effectively address these two research questions. Yeah. So the reasoning on graph, this is our latest work, which have recently been accepted by the iClear 2024. And in here is also a retrieval augmented paradigm, retrieval augmented framework. But in here, we try to utilize the LLM, the planning ability of the LLM. So for the better knowledge retrieval. So in here, for example, given the question, who is the child of the Alice? Ideally, as a human, in order to answer this question, we can first come up with a plan, and then we can execute this plan step by step to get the final answer. And in here, in the knowledge graph, basically the relation path, which is a sequence of relation, can be served as this kind of faithful plan for conducted reasoning. For example, who is the child of Alice? To answer this question, we can have a two-step plan. Step one is to find the person that Alice is married to, and step two is find the child of that person. So this plan can be expressed as this relation path, married to and father of. And after we execute this plan on the knowledge graph, we can retrieve actual reasoning path like this: Alice married to Bob, and Bob is the father of Charlie. And then we know that the Charlie is the final answer. So in this way, we can find that we retrieve the knowledge based on the plan, and we organize the retrieved facts as a reasoning path. In that way, we can achieve both the effective retrieval and also fully utilize the structural information inside the knowledge graph for the reasoning. Yeah, so here is the framework of here is overall framework of our method. So given the question, we ask a large language model to generate lots of relation paths. This path will be used as a plan, and we retrieve the relative facts in the knowledge graph based on the plan. Retrieve lots of reasoning paths on the knowledge graph based on the plan. Yeah, for example, in here, like Joe Biden was born in a city, and this city is a city of United States. So after we collect lots of reasoning paths, we use this path as a context and ask the large language model to conduct the reasoning based on the path. So in that way, we can fully utilize the structural information inside the graph to hint the large language model to conduct the reasoning. This method has been shown quite powerful in some complex reasoning tasks like multi-hop reasoning. Yeah. So external results show that our method successfully suppressed the existing method in this kind of knowledge graph question answering task. And also our planning module, which basically we ask the large language model to generate the plan and retrieve the reasoning path. This module can also be plug and play with other LLM to improve their performance. This shows that our method can achieve a quite good result in the retrieval stage. Yeah, so last is our method can show quite good interpretability. For example, by giving this kind of reasoning path as the context, the large language model can answer the question and also provide the explanation for this kind of reasoning. So in that way, we can not only conduct faithful and reasoning, but also can provide interpretable result for the reasoning, how the large language model get to this kind of final answer. Yeah, and so for the second part is the LLM augmented knowledge graph. So how can we utilize the large language model to help? How can we apply the large language model to help the application in the knowledge graph area? So one of the typical tasks in the knowledge graph is called knowledge graph reasoning. Yeah, because as we all know, the knowledge graph are often incomplete. There are lots of missing facts in the knowledge graph. And how can we leverage the existing structure within the knowledge graph to derive new knowledge and new insights? That is the definition of the knowledge graph reasoning. So the large language model can definitely be helpful for this kind of knowledge graph completion task. The most easy way is to use the prompt to ask a large language model to predict the missing facts. So in here, we can design lots of knowledge graph prompt, and we can transfer the structured knowledge in an unstructured format, and then we can ask a large language model we can ask a large language model to predict the missing facts. So for example, in here, we want to predict the possible tail for this kind of triple, and we can gather some future example about this Charlie Angelus from the knowledge graph, and we can use them as context. Then we can ask the LLM for the kind of knowledge graph completion task. So that is quite a naive way to utilize the LLM in the knowledge graph domain. But I think there's still some challenge is that LLM are very good at processing the text, but when we face this kind of structured knowledge, the LLM are not good at understanding the structured information. And also, if we directly ask the LLM to predict the possible tail or possible facts, we can still suffer from the hallucination problem, and we do not know whether this kind of facts are correct and how the LLM generate results. Yeah, so in order to solve this problem, we want to present another paper of our work called a chat rule. In here, instead of asking LLM to directly generate the possible tail, we ask the large language model to extract some meaningful logical rule from the knowledge graph. So the logical rule basically is a combination of relation, and this kind of rule can be used to derive new knowledge and new facts from the knowledge graph by using some existing reasoning mechanism like a forward chain reasoning or backward chain reasoning. So the reasoning process of this kind of rule-based reasoning process can be easily interpretable and understood by the human. So in this way, we ask the LLM to generate rule and apply the rule for the reasoning. We can harness both the ability of the large language model in the rule generation and also harness the interpretability advantage of the rule-based logical reasoning. Yeah. So here is a framework of our paper, of our method. So here, given a knowledge graph, we can use some random walk to sample lots of rule samples from the knowledge graph. And then we ask the LLM to generate the possible rule based on this kind of sample examples. And after that, we can have a set of candidate rules. But for now, we cannot directly use them because the LLM can do some hallucination and some of the rules might not be meaningful. So in order to validate this kind of rule and also assess the importance of them, we propose a rule ranker mechanism. Basically, we'll apply this rule back to the existing knowledge graph and to test the coverage rate and also the support rate of this kind of generated rule. And after that, we can get importance scores of each rule. In this way, we can easily remove some unmeaningful rule from the candidate sets. And after that, we can use a kind of rank rule for the logical reasoning and generate some new facts. And all the reasoning process here are deterministic and also understandable by the human because we conduct the reasoning based on the logical rule. Yeah, and here is and for the rule generation, basically, it's also a prompt-based method. So given a definition about the rule and also some future example we get from the knowledge graph, we can prompt the LLM to generate lots of candidate rules. Yep. And here we test the performance of our method on lots of large graph completion benchmark data set. And the experiment shows that our methods are quite effective compared to the previous rule mining methods. Yeah, and also the cost of our method is also quite low here. So from the result, we can see that we can mine the rule with less than $1. And also we can see we generate lots of meaningful rules. For example, the husband, in order to predict the relation husband, then it's definitely helpful to find the inverse relation of the wife. Yeah, so besides this kind of knowledge graph completion, we can definitely use large language model for the knowledge graph construction. So conventionally, to construct a knowledge graph, it actually involves lots of different techniques like name entity recognition, entity typing, entity linking, and this kind of, firstly, for each of these tasks, we can design a method to solve them. But for now, with the large language model, all of these tasks can be handled with only one large language model, and this can it can speed up this kind of knowledge graph construction process. For example, there are some pre-trained LLMs that specify for the knowledge graph construction task. In here, for example, we have no LLM. In here, we can conduct both the NER problem, event extraction problem, and also the relation instruction with only one model. And we can use different instructions to conduct different tasks. Yeah, so the last part is how can we synergize the LLM with the knowledge graph? And unfortunately, there are not much existing work in this area, but I think I can point out two very promising future directions. So the first one is called LLM as agents. And in here, I think there are two existing work in this area. The LLM as agent basically to consider the LLM as an active agent, like a human. It can dynamically conduct the searching on the knowledge graph and to get the results of and conduct the reasoning process on the knowledge graph. For example, given the question, which country Barack Obama from, and as an LLM, we can start from the Barack Obama. This is the entity on the knowledge graph. And then we can search for the next hop entity in here, which Barack Obama was born in Honolulu, and the next hop is Honolulu is the city of the United States. So in that way, all the reasoning process are transparent to the user because they are conducted on the knowledge graph. And also this kind of method can be conducted in a pure prompt-based, so it do not require any training, and it can be applied to different kind of question and knowledge graph. And that is the pros, but the con is because this kind of LLM agent require the LLM to make decision, so it requires multiple LLM inference, so that can lead to a very high latency and a very high cost. Yeah. And another promising direction is called a multimodal graph LLM, and this is one of the topic I'm studying right now. So in the vision language domain, we have lots of vision LLM that can directly understand the vision, the image. But can we have a similar graph LLM in the knowledge graph LLM domain? In here, given a knowledge graph, we can input them into a graph encoder and get lots of meaningful graph representation. Then we can ask the questions about this kind of, we will feed this question, user's question and a graph representation into the large language model. And we can ask arbitrary question regarding to this graph. And in that way, we can enable the LLM to understand the graph structure and fully utilize the information in the graph to conduct the reasoning. Yeah. I think that's pretty much for today's presentation. So yeah, if you have any questions, please feel free to ask.
Thank you very much for this very rich and dense talk. I'm sure we're going to have questions in the room and probably online as well. Who wants to start? Nicolas.
Yeah, thank you for your presentation. Could you come back to the slides about LLM enhanced, KG enhanced LLMs, so your first demonstration board? I was wondering what kind of data was used when you tried those Yes, so slide 26, I think it was. Yeah. For that kind of data, the way you from a question extract answers directly from the LLM. So that's not natively in the LLM like OpenAI, ChatGPT and such. Do you have to do some retraining to allow it to extract this from the graph?
Yeah, so that's a very good question. So basically, if you look at these frameworks, actually the knowledge retrieval can be separate from the large language model. So in here, we can have lots of different knowledge graph retrieval. For instance, the most easy one is entity linking. So in here, given the question, we can identify an entity, which is Barack Obama. Then we can search all the facts related to Barack Obama in the knowledge graph and use them as the retrieved knowledge. And after that, we can construct a prompt. Like the first part is the information we retrieve from the knowledge graph, and the second part is the question. And we can ask the large language model, please answer the question based on the facts. In that way, we do not need to retrain the large language model. They can be the large language model can be used to conduct the only be used to conduct the reasoning, so that we can apply this kind of method to arbitrary large language model like ChatGPT, which is a closed source LLM. We cannot conduct the retraining, but also definitely you can conduct some fine tuning, because as we shown in the figure, after you get the answer, you can optimize both the knowledge graph retrieval and the LLM to help them better retrieve the knowledge and better conduct the reasoning based on the fact you retrieve. So this, I think, this kind of paradigm called retrieval augmented LLM training.
Thank you. And as a follow-up question, so when you show your results later in that part, where you improved the power of different LLM systems on QA datasets. So it's not just your method that you injected, since you must have injected a knowledge graph, a knowledge basis at the same time. What kind of knowledge base did you use at that moment?
I think in here the data set is based on the free-based knowledge graph.
Okay. Thank you.
Yeah, thanks.
Well, I do sort of have a follow-up question too. Well, thanks for your presentation, first of all. If you go to slide, I think it's 31, where you use the LLM to generate relation path. I was wondering how suited general LLMs are to generate relation path. I mean, they were not trained for this, so what's the quality of the result here?
Yeah, that's a very good question. So the short answer is, without training, the LLM cannot generate the relation path in the knowledge graph, because they have zero knowledge of what kind of relation has been stored in the knowledge graph.
Yeah, sure. They don't know the schema.
Yeah, don't have the schema. So in here, you can see that we have a planning optimization part function here. Basically, we distill the relation information and the combination of this relation information from the knowledge graph into the LLM through this kind of planning optimization. So after that, the LLM can generate a very good relation path. But I do not include this kind of optimization details here, because they're related to some mathematical formulation.
Okay, thanks. No, I missed that loop, which is why I was surprised by the capability of LLMs to generate relation path. Okay, thanks.
Yeah.
I have a question too. Can you hear me? Right.
Yeah, so I can hear you.
I have a question about prompting. Do you have a methodology for prompting? Do you optimize prompt at any step using, for example, frameworks like DSPy?
Yeah, I think like the prompting is kind of quite important here. Yeah, definitely. How to optimize the prompt is so to have a better prompt is definitely very helpful in this kind of prompting-based method. So in here, basically, I have tried lots of different prompts by giving the definition of the task of the logical rule I try to generate it, and how many like few short sample I should provide it in prompt. Yeah, and I think like the package you have mentioned is also quite good. It's quite powerful, and also I think instead of using that package, I think you can also try different kind of technique like chain of thought prompting or tree of thought prompting. And yeah, I think there are lots of different more advanced prompting methods instead of only focusing on design, the structure, and also the word you use in the prompt.
Yeah, thank you. This answers the question. I think yeah, LLM, the prompt engineering part is very important, and we can use large language model to optimize the prompt engineering part.
Yeah.
Some other questions here? I have one. At the beginning of the talk, and also we know that in fact the knowledge that is encoded in knowledge graphs is valid at some point in time. So, but you have not talked about the validity of the time, of the temporal information in this presentation. Can you comment a little bit about this problem of time and the validity of information?
Yeah, that's a very good question. And also, I think that's also one of the research direction I'm focusing on right now, because as we all know, the knowledge graph itself are dynamically updated. So there are new facts have been added and there are old facts has been deleted. So in that way, how can we model this kind of knowledge updating information in the knowledge graph, and how this kind of information can affect the knowledge in the LLM? So I think we split them into two parts. So the first part, if we only focusing on the LLM part, we call them as the LLM knowledge editing, because when a new knowledge has been added to the knowledge graph, we can easily extract it from it, and we try to update the information of the LLM based on this kind of new knowledge. So in that way, we're trying to update the knowledge stored in the LLM parameters, and that is one way to do that. And I think there are some there are lots of it's a quite popular research directions in this area. So how do we edit the knowledge inside the LLM with like maybe a very lightweight manner? And in here, the knowledge graph can be used to provide what kind of information should be updated. And the second part is because the knowledge in the knowledge graph can also be updated, and also there are some like time correlation inside this kind of knowledge graph. For example, the temporal knowledge graph. There are for each event, for some event, there are some timestamp. How can we capture the temporal correlation between this event to predict maybe new fact or new insight? And I think one of my colleagues are conducting this method following my paradigm. So in here, we can extract some logical rule, but in here, we do not consider the timestamp information. But we can also extract some temporal logical rule with the timestamp injected in the rule space, so that we can like extend our method to the temporal knowledge graph and consider the temporal information in the knowledge graph for some reasoning task, like the predict what event will be happen next based on the previous information.
Yeah, reasoning on knowledge graphs with time is extremely complicated. And I think it's not a solved problem. And so I guess adding this to fusing information with LLM is another layer of complexity. But thanks for this answer.
Yeah, thanks.
Other questions here?
Yes. Did you evaluate the complexity of your of the knowledge graphs enhanced with the LLMs from a formal from a formal language perspective, for example?
So when you refer to the complexity, do you mean the computational complexity, or so what kind of complexity do you mention?
Yes, the computation complexity.
You mean this method or?
Yes, for chat rule.
Oh yeah, so I think the chat rule, the major complexity come from the rule generation, because in here we need to call the large language model to conduct the inference. Yeah, basically all the major complexity come from the large language model during the inference stage. But in here, because for the ChatGPT, we can use its API, so it's not our concern to do that. But after we generate the rule, all the remaining process can be quite speed. It's quite efficient because there are lots of existing package have been implemented, and also for the rule generation part, we can conduct like the parallel inference, because we can split this kind of query into multiple different queries and ask LM to generate to get a response in parallel, so that the overall the training time is not hard, but the inference of LM is still quite intensive here.
Mm-hmm. Did you try for the you mentioned the ChatGPT cost? Did you try experiments with open models like
I think I do not include the result here, but in the paper we actually tried different LM like Llama and also Mistral. I think most of them can still achieve a quite good result. But and also a very interesting thing is that we also tried GPT-4, but the performance of GPT-4 are not good as the GPT-3. Yeah, so we assume like maybe the more complex model tend to because due to this kind of complexity during the inference, they are more intent to stop to early stop, which lead to a fewer rule generated by the GPT-4, and that lead to a poor performance. But I think you can refer to the paper. We have the performance about our method on different large language model.
Thank you.
Yeah, thanks.
Thomas, Victor, Margot, questions on your side?
Yes, I have one question. Thanks a lot for the presentation first. And I have just a question regarding the size of the graphs. Did you notice any limitation the bigger the graph gets?
You mean the chat rule?
For the chat rule, yeah.
Yeah, so actually for the chat rule, we do not have such a limitation about the graph, because as you can see, we do this kind of a rule sampling. This can be conduct, it's because it's a sampling mechanism, and we can extract this kind of rule from a very huge knowledge graph. And then we will always feed into the knowledge graph with just some rule samples. So regardless of the size of knowledge graph, we can still get the samples, and we can be feed into the LLM into the context.
Okay, and have then maybe a question related to that. When you use the graph to enhance the LLM, have you tried some more difficult query that is involving more relations, so that you might come to the limit of the context size of the LLM?
You mean for the question answering task or for the rule generation?
No, for the question answering task.
I think
basically, do you have some example where the size of the input you should give into the prompt could be too big?
Yeah, I think that's a very good question. So one of the limitation of the existing retrieval method is that so when we retrieve the facts, they can easily exceed the context size. So especially when the knowledge graph retrieval are not good enough, we can retrieve lots of irrelevant information, and it can easily exceed the context size. Yeah, I think that's definitely the limitation here. Okay. But like with a better retrieval, we can make sure we only retrieve the useful information and then make sure it can be fit into the context. So that's the reason why we need a very good retrieval here.
Yeah. Okay. Thanks a lot.
No worries. I think another follow-up answer is that so instead of using the retrieval, basically we feed the retrieved fact in a text. Maybe the multimodal LM could be the future, because we can compress the knowledge graph into some embedding. Then in that way we can compress lots of information and represent that with maybe a few embedding tokens. So in that way, it provides more flexibility and more scalability of this kind of method. Yeah.
Do you hear me?
Yeah,
Thomas,
I
on
can hear you.
t'entend pas. Vas-y.
I try to change my settings. Is it better now?
Ouais.
I can hear you.
Yeah, you hear me. Actually, I was wondering if we could make the knowledge to be actually there are many methods to encode knowledge in vectors. It's known as knowledge graph embeddings. Maybe I was wondering if it's possible to inject knowledge graph embeddings into the prompts as soft prompt to the LLM. I saw that there is a knowledge graph LLM pre-training in your talk, and I want to know, yeah, this is this part. Is it possible to say more about this?
Yeah, that's a good question. And I think this is also the research I'm conducting right now. So like I mentioned, we can give large graph, we can have a graph encoder to get the representation. And definitely the large graph embedding is one of the most simplest encoder here. We can encode the large graph into some embedding, and we can feed the embedding into the LLM. And for now, I think the answer is this is doable, but the performance are not easy to reach to achieve. So because unlike the vision language, unlike the vision domain, we can have lots of pre-trained vision encoder. In the graph domain, we do not have this kind of generalized pre-trained vision encoder. So that leads to this kind of, we call that as an alignment problem. We try to align the representation of the large graph into the representation of the large language model, so that the LM can understand the large graph embedding. So I think for now, there are still at least based on my experiment, there is still a gap about aligning the graph representation with the LM representation. So, but once this kind of alignment is finished, then we can definitely input the graph embedding into the LM and conduct the reasoning. And I think there are also some work in this area. But I think one insight I can have for now is that, so if we only try to align some node embedding, for example, a single entity, that could be easy, and there are some work has been achieved in there. But if you want to align the graph embedding, basically is a set of node and also set of relation. At least for me, I haven't achieved that yet. Yeah, but I think there is a future here. Yeah.
Okay. Do we have other questions? Well, Linhao, thank you very much for the talk and for all those answers. We'll get a better understanding of all this, and we're going to rush on the paper to read it again, given the information you gave us this morning. Thank you very much. And I will share with you the link to this recording, and we'll keep talking. Thank you.
Yes. Thank you. Yeah, thanks for the invite. See you.
Okay.
Thank you.
Goodbye.
Thanks a lot.
Bye.
Bye-bye.
Bye.